In this video, I want to introduce the idea of stack-based memory. So stack memory is the memory it's used for functions. When we say stack, what we're basically referring to is, it's a data structure that basically represents functions calling functions. So the way a program flow really typically works, right, in C is you start at some place called main. Main itself is a function, and main will require some memory. Then we have another function, right? Maybe main calls something like, oh, well, here in the example, it's called bar, right? Main calls something else. New function. Function has new variables inside. Could be parameters, could be local variables. Point is, it's going to need new memory. So we have to request that somewhere. And then maybe that function calls another function which also needs memory, and then that one calls another one, another one, another one. They each need memory. We need some way basically to manage that. And what they propose, what is used, is basically the idea of a stack, where every element you push on a stack is something called a stack frame. And it's something that basically is a place to store all of the data needed by a particular function. Now you may wonder why are we talking about storing this stuff in a stack, right? And stack, right? Conceptually, you think back to when you took data structures and algorithms. A stack looks something like this, and what we're proposing is every time I call a function, I basically push on this request for memory to store variables. So if I have a stack here, right? Maybe I have my main here, and then if main calls something else, I do another kind of push, and I have memory for bar. If bar calls something else, I would have another thing above it. That's kind of the conceptual thing going on here. That's what we're proposing. And each of these little bits here, that's the thing I'm actually going to call a stack frame. I won't go too much into detail of stuff. Hopefully you've seen these ideas in other courses like computer organization or computer architecture. But this is what we propose and what is used in order to manage memory for a program, for the functions inside of it. Now you may wonder why a stack, right? I mean, we also had the option of a queue. That wasn't the common data structure that was discussed in the previous courses. Well, the answer is, well, a stack basically mimics how functions persist. So main runs, then bar runs, and when bar finishes, we jump back to main. So even though I have this code here, right, and bar really jumps me back up there, once I get to the end of bar, I jump back to main over here. Basically, I go after that line. And so what it turns out is if we start thinking about this, it mimics this effect of a stack. So at the bottom of my stack, I have a function, main. Then the function that it calls is on top of it. And if I have another function, I push it again and again and again. So it's basically tracing a list of who called who. And when I do a pop, I'm always getting rid of the most recent function. Right? I want to get rid of the thing that's kind of outside, the most recently run code. It wouldn't make sense for me to get rid of something like main that's at the very bottom of that stack because main is, it's still running, right? It's basically delegated functionality to other functions, right? Other functions that contain program code. And so we definitely want to leave it there. The only thing we can ever release memory for is whatever functions on the top of the stack because nobody is, dependent on them. They're kind of off by themselves, the topmost thing. They're not waiting on anybody. Nobody needs stuff from them. They just have a return value perhaps that they're generating. So we end up using a stack. And we'll basically say that when a function is run and we need memory, we'll push a new stack frame. And when it's done, we'll release a stack frame, right? And then we get the memory back from it. The nice thing here about stack in comparison to, there's the comparison I guess we'll start with is static memory. Static memory is stuff that's around for all of time, which is a little bit problematic because then that means that, I have to have this memory, I need to keep track of this memory forever, right? And it has a chance, right, that we use up too much stuff, right? Stack memory, right, is dynamic. It's dynamic in the sense that as functions are called, as they're returned, the stack will grow or shrink. And it'll do that automatically. So basically, when a function exits out, we can look at the stack and say, okay, hey, all the memory for this function existed here, and so we'll just pop that off and release it so somebody else can use it. There is kind of no question. It's just automatically done. And for C, that's actually very nice, is automatic deallocation. Because later when we get to heap memory does not have automatic deallocation, right? It's not automatically freed at the end of a function or at the end of a program's execution, like for stack memory. It's only freed when we say it is freed. Okay, so that's the basic idea of stack memory. Let's take a look at a little simulation here. So I have this little chart here, and let's say at the beginning of time, I have something like main, right? So main is a function running. Initially, what I have to do is reserve memory for everything that the main is going to do. In this case, main doesn't have any parameters. It just has one local variable. It has the number 1. So kind of a first pass would be, hey, we're going to create a stack frame here that contains all the memory that's needed by main, primarily just I there. So what happens then as this thing runs? Well, that memory on the stack, right, that stack frame, is the working place for this function to do stuff. For example, set I to 1. So all of a sudden, right, that variable updates, and okay, that memory is being used. Again, this is the purpose of the stack, right, of stack allocations. It gives this function a place to do its stuff, right? It gives it memory to work with. But then what happens when you call something? So this next line here, right, the third line in main, is going to call the bar function. What happens? Well, in this case, I need to allocate memory for bar and its parameters. I'm allocating memory for bar itself because it has a return type. So if I'm running bar, I know that at some point something should be computed to me that I return and which is then used by main. So for sure I need to have some memory allocated for the end of bar. And that I have on the right hand side with some dummy value in there. Reason being, that particular memory allocation, right, I'm not going to know what value it has, or well, I'm not going to be able to give it a good value until that function actually runs, because I need to compute what is the result so that I can store it somewhere. When the function first runs, when bar first runs, I don't know what exactly its result will be, so I can't put anything useful there. Now for J actually will be populated. So J is the name of the parameter going to bar, and we need to allocate memory for it because it's a parameter variable. So it's something that's being passed in. It's basically going to be a local variable for that bar, and it's taking its value, right? It's copying its value from the I variable. It's being passed as a parameter to bar in main. So then bar has its own local variable called J, containing a copy of I, which is 1. Okay. Now we're not done allocating the stack frame for bar yet. We also need to grab memory for k. So k is the local variable inside of bar, and k is set equal to 2. So it's just going to be used as part of the computation. So then I have basically my stack frame for the function called bar. If I go through this, I can basically page through the code and see what happens. So let's go here, j equals j plus k, so we can see j increments over on the right-hand side. Then we go over here to our return. Our return statement, notice that it allocated the part of the stack frame for bar, and that's this thing here. This is all bar. It allocated that, well, excuse me, it assigned the memory that was saved for bar's return value to the value of j, because that's what the return statement is saying. It's saying, hey, when bar completes, I want to return the value of the value of j, so that 3 that was in j, that gets copied into that memory reserved earlier, that part of the stack frame at the very bottom, that was reserved for the return value from bar. Now that bar is completed, we can now think about actually popping it from the stack. So I free those two variables, right, j and k. Bar is still going to persist for a little bit because its value needs to be read by main and stored into I. Then we jump back to main, right, and main can basically say, oh, hey, the function completed. I know its return value is just above the stack frame I'm using, right, because main has a stack frame itself, and the stack frame for bar would have been just above it. So I can glance up, see the return value is 3, and store it into I. And so then, right, we've basically done a computation using that function. And so hopefully you saw it in there, is basically we grew upwards, right? We allocated memory for the function that was being called, it did stuff, and then when it was done, we deallocated, right, and moved it back up. Moved it back down. So it was going up and then down, just like a stack. And then kind of there's this little areas right that I've highlighted, and each just represent the different stack frames, right? The memory that was just for bar versus the memory that was just for main. So this is how the memory allocation works for stacks. Again, the idea is this all happens automatically based on functions being called and functions returning. So very nice. Now, just to add some little more technical stuff to this, the way this looks inside, if you think about your hardware, is there are actually some registers that keep track of what's going on. So let's say, right, your program is running, there's 2 pointer registers. First is a stack pointer, second is a frame pointer. What the stack pointer is doing is it's basically keeping track of the top of the stack. So I have a little arrow over here, top of stack. So that, for me over here, would have been something like, this over here. SP was over here when bar was running. Stack pointer is pointing at the top. Because basically we want to know how much memory have I used on the stack. So that's kind of a common register that we have in CPUs, is to keep track of the top of the stack. And as things get called, basically the stack pointer can move. So in this example here, what's happening is I have a function. Let's call this function A. And that function is actually going to call in the function B. I'm labeling this over here on the right-hand side. Now, initially, right, if A is the only function around, SP, right, the stack pointer is basically pointing at the top of A, right? This is all the memory I've used up so far. But then, what happens if A wants to run something, wants to run function B, well, then basically the stack pointer is going to migrate upwards. Here you can see we're reserving some, basically some data, right, or some storage to store the return value. Or the return address, right? Basically saying, okay, I need to know stuff like, for example, either what does B return, or maybe I could also have, where in A I left off. There's actually kind of different pieces of information that might be stored here. In the slides, it just says return value, but there could be a few things here. And then, right, maybe B runs, and so B has a new stack frame, and it gets pushed on top. And when it does that, the stack pointer gets moved up. So stack pointer is always supposed to be pointing at the topmost frame, right? Where exactly is the current function located in the stack, right? Where is its memory being used? And that's useful, right, so that we can easily kind of jump down and maybe access the variables that are stored in it, or maybe access if there's program code on there or something else. We can get at it easily. And then the frame pointer, FP, over here on the left-hand side, right-hand side, basically it's going to keep track of where was SP. So notice that we went from over here, SP was at that arrow, now it's FP. So it's pointing at basically the end of the stack frame of the most recent thing. And so it basically just follows SP. The idea being is when you exit a function, you can basically do something like SP equal FP, right? You can unroll that stack or undo something on that stack by just going back to the previous frame pointer. And treating that as your stack pointer. Basically what happens, right, is it all of a sudden saying, oh, now reference the data underneath it, do stuff according to whatever that data is supposed to be for, and just ignore the fact that there was an old thing up top, right? We're just going to leave that other stack frame alone. We only care about what's below the current stack pointer. Okay, so that's what you're going to see in hardware, right? If you were to look at this, there's these different registers that basically track the stack moving up and down. It's just another moment talking about this. If I want to draw the full picture, this is how it looks, right? Start with the first call, has a stack frame, has some sort of return information, and call something else, right? Has another stack frame, has a return value, and generally what happens here, this is kind of the new bit for this slide, is that hey, FP is just one register, so if I have to call multiple functions, well, and I don't want to basically replace it over time with SP's value. What happens is that I need to basically flush that frame pointer to the stack. Basically say, okay, for this most recent frame that I've pushed on there, I'm going to save a copy of the frame pointer before I replace it with something else. If I call something again, basically I do the same thing. Because I only have one SP register, right? So I need to basically store references downward, right? So references saying, oh, go over here, versus go over here. Because I only have that one SP, I only have that one FP register. I need to sometimes save its result back into the stack in order to let me call more than one function. If I just have one function, I'm actually just going to be able to do stuff as the kind of the previous slide had it, and just grow up and then go down. But here, right, if I have multiple functions that would be pushed on, that means that my FP and SP are going to be moved a lot, and so I need to preserve their values, right? And I only have two registers. Well, I need to have some place to put that. All right, so that's an overview of how stack memory works. Very nice in terms of automatically handling allocations and deallocations.